Good morning, everyone, and welcome to the academic part of the program. I am Lavi Singhal from Peking University. So our first speaker for the morning is Professor Stefano Luzzatto from ICTP. He'll start his mini course on hyperbolicity and physical measure.
It's very nice to be here and very nice to see you all. I'm Stefano Luzzatto. I'm one of the organizers, but it's also the very first time for me here, very first time in India, so it's a new experience for me. It's the first time I've been in a lecture theater which has a bigger blackboard than the one at ICTP, which is my institution. And so I'm very impressed indeed, and it's very nice facilities. Thank you so much to Rajesh and the whole team here for hosting us. I think it's an ideal place, an ideal facilities for us to have this week. And as Rajesh said, and as one of the organizers, I also cannot but repeat that what we really want from the school is to make it possible for interactions between younger and older participants, amongst younger participants, between older participants, all interactions in all directions. It's an opportunity for us to get to know each other socially and also to learn mathematically in an informal setting as well as the formal setting of the lectures. So there's going to be, for this week, the 2 weeks of the course are slightly kind of focused. Okay, so this first week is going to be a little bit more focused on differentiable dynamics and hyperbolic dynamics. The second week is going to be a little bit more focused on homogeneous dynamics. So some of the lecturers, including me, for example, are not unfortunately going to be able to stay here for both weeks. I think many of the participants will, and I hope that the 2 weeks will be anyway not so far from each other. So I hope that both, those who are able to stay both weeks will be able to follow and be able to take advantage of all the topics. So this first week has 3 kinds of lectures. There's going to be 2 mini courses, one by myself and one by Sylvain Crovisier, who will start his mini course later on this morning. And then there will be some kind of full 1 hour or 45, 50-minute lectures by some invited speakers. And then we have decided to try to give as much space as possible to younger participants who wanted to give a little bit of presentation of their work. So we're going to have some of those lectures as well. We hope that we have not packed the schedule too much and that there will still be enough time to relax and take advantage of the swimming pool and other things here. Okay, so the mini course that I want to talk about, I will start with a kind of 3 main concepts, which I will then define later on today. So, and the relationship between them, which are really the theme of the mini course and the theme of many of the lectures that you will hear. So the first concept is one that you should all at least have heard of before, which is just that of a dynamical system. Okay, which can be a continuous time or discrete time. And this I don't think I would need to define. And the related concept that will be very important here is that of a physical measure. And this I will define below. And physical measures are a way of describing dynamical systems, some dynamical systems. And we have here a quite well-known conjecture called Pahs conjecture, because it was kind of explicitly formulated by Pahs, who is a Brazilian mathematician, that basically says that typical dynamical systems have physical measures. Because we know that examples of systems that do not have physical measures, and when they do not have physical measures, they're kind of pathological examples in some way. So this is a conjecture which may or may not be true, but in any case, it has guided a lot of research in the last few decades, And I think it provides an inspiration for working for a certain approach to dynamical systems. So the way one fundamental concept that somehow constitutes a bridge between these two is that of hyperbolicity. So hyperbolicity, you could say, is a state of mind, rather than in the sense that there are many different variations, there are many definitions of hyperbolicity. It can get a little bit technical, and the exact theorems you prove depend on exactly what you mean by hyperbolicity. I will give some heuristic definition, and then as I need it, I will give some more precise definition. But for the moment, let me say that the way it constitutes a bridge is because we believe, and there is a lot of evidence, that in fact hyperbolicity is the key ingredient, is one of the ways in which you can get physical measures, and this is also takes the form of a conjecture. This is sometimes referred to as the Viana conjecture, is that hyperbolicity implies the existence of physical measures. So this is one path through which we can approach the Pahs conjecture, and I should say that in this direction there is really a lot of work from the 70s. I will say a little bit more about it later, but there's also been some very recent work, and I could say that we are pretty close, you know, within a few years probably, depending on exactly the form of hyperbolicity that we mean. There is really essentially affirmative answer to the Viana conjecture. So what is missing, of course, here is that if we want to use the Viana conjecture to approach this, then one of the problems is to show that typical systems are hyperbolic. All right, this is one way that you could approach this. And in other words, the general concept of verifying hyperbolicity. Right? So here the question is, can we verify, can we show that some systems are hyperbolic? And this will actually be the main theme of my mini course today. So this is an aspect that is quite difficult. There are some kinds of hyperbolicity, very strong uniform hyperbolicity, in which we can easily construct examples. But that's a very special case, and it's certainly not typical. If we are hoping to have a version of hyperbolicity that can be satisfied by typical systems, then you really need a very weak form, which in general is not robust, and it is non-trivial to verify hyperbolicity. So this is going to be, and therefore it's not a kind of topic that many of you are likely to have really heard of. However, there is some interesting work in this, and there's some new ideas and new techniques, and this is going to be the focus of my course. However, today is just an introductory lecture, so today I want to give a general setting. I'm going to talk about this problem in the setting of a very specific class of maps, although the techniques I'm going to introduce, I hope, are useful and are relevant to other classes. And this class of map is the Lorentz equations, which really have formed a kind of, have been a family of dynamical systems which have been relevant from the 1960s on in the field of dynamical systems, have motivated a lot of examples and a lot of theory. So I am going to discuss today just a little bit of background, okay, on this. So where did I leave my notes? Yeah. So let me first say a little bit about physical measures, because after all, that's really what the goal is about. Okay, and then we'll talk about hyperbolicity and the Lorentz attractor and how it works in the Lorentz attractor. So what is a physical measure? Well, if we have a dynamical system, so suppose M, some of these definitions will work even for general metric spaces, but for let's assume it's a Riemannian manifold, compact Riemannian manifold, to make things a little bit easier. Suppose we take a point, a so-called initial condition, then of course the general goal of dynamical systems is to look at the forward orbit of the point x, which we define like this. This is just the set of points under iterations. And we want somehow to describe this orbit. So I'm starting the very, very basic level of what it means to study the dynamics of a dynamical system. We want to somehow describe the structure of this orbit, perhaps describe how this structure changes as you perturb, as you change the initial condition, or as you change the map itself. But fundamentally, this is the object that we want to say something about, right? Because this is the evolution of the system. So there are various ways to say something about this. As you know, in some sense, the most immediate one is a topological description. You may say, what is the omega limit? What are the topological limit points of this? We want to take here a measure theoretical point of view. And so we want to define a sequence of probability measures in this way. So this is going to be really a fundamental object, so we'll take a few seconds to reflect on this. What this is saying is that we have our system here, we have our initial condition x, we have our iterates, let's call this x0, x1, x2, x3, and so on, right? And we're putting Dirac delta, this is the Dirac delta on each of these points, and we're taking 1 over n. So if we take the first 1,000 points, we're putting 1,000th of the mass on each point, right? And we're defining a probability measure that's defined exactly like that. So if you take some set here, A, and you want to measure the measure, mu n, so this is a measure, or maybe this notation is not ideal because it's not the measure of the point x, right? This is the measure mu n of x of the set A, right? Is just the proportion of points inside A up to time n, okay? So the total measure of the space is always 1. This is a probability measure, and it tells you more or less where these points are distributed. So you can imagine, suppose you have 1,000,000, suppose n is 1,000,000, so you have 1,000,000 points in your space. It's very hard to keep track of exactly where each point is, but if you look at this measure, it's going to tell you where these 1,000,000 points are concentrated, right? So if these 1,000,000 points are clustered around this region, then this is where you're going to see most of this measure, right? So this measure is really describing the way these points are, the amount of points, the proportion of points that are in different regions of the space. So we have a sequence of probability measures, and we're interested in what happens to this sequence, to the limit points of this sequence. Does this sequence converge? So the fundamental question is, does mu n x converge? You think it converges? So it may or may not converge. And the convergence, if it does converge, then it's clear what it's doing, right? If it does converge, then it is describing the asymptotic distribution in space. So convergence of this measure means that when n is, it means there exists a measure. So if mu n x converges to some mu, in the sense of measures in the weak star topology, then it means that there's some measure on your space, right? Some distribution of mass, and this orbit is visiting various regions of space in a way that is precisely described by this measure, because it means that when n is very large, these two measures are very close, and that means that the distribution of orbits is really well described by this measure. And the larger n is, and the better described it is. Okay, so the convergence means really that you have found a way to describe statistically or probabilistically the behavior of this orbit in a good way. So there's some very simple examples. For example, if it's easy to see that if you have an orbit that converges to a fixed point P, if you have an attracting fixed point and you have the convergence, then when n is very large, 99% of the points are going to be in an arbitrarily small neighborhood of P. So it's easy to see that in this case, mu n of x converges to the Dirac delta in P. So this is a simple convergence. Okay? Another setting where you have convergence, of course, is when you have an invariant, if mu is an invariant ergodic measure, then it is a classical Birkhoff's ergodic theorem says that for almost, okay, then we have that mu n of x converges to mu for mu almost every x. Okay, so this is a situation where if you have an invariant ergodic measure, you might not know exactly for which points this holds, but there is a non-empty set of points for which this converges. Okay, so mu describes the statistics of the points. However, there are also counterexamples. So there are easy counterexamples where this does not converge, and the non-convergence is even more fascinating, actually, than the convergence. So what are some counterexamples? Well, imagine that you have a symbolic dynamics, that you have a shift dynamics, for example, right? Or you have a map. So I presume most of you are a little bit familiar, so I would not go into the details. Suppose you have F has a Markov partition. Right, or can be coded, i.e. has a symbolic dynamics. Okay, so for those of you who are not very familiar with this, it means that you can code, you can conjugate it to a system, the symbolic system, where you can just take, for example, zeros and ones, and you can code all points by zeros and ones, okay? So imagine you have that system, then it's very easy to find points for which this does not converge, because imagine you take, because you can choose, you have full freedom in choosing your sequence of zeros and ones, right? So suppose you choose a sequence, you choose a specific sequence that has a bunch of zeros, right? For example, 10 zeros. So it looks like it's very close to the 0 point, but then you put 100 ones, okay? So then after 100 ones, the proportion of ones is 90%, but then you put 1,000 zeros, okay? So then if you look from the beginning to the end, you've got 1,000 zeros, 100 ones, so it looks like with 90% of the time is close to the point 111, and then you put 1,000,000 zeros, and you keep going like this, and you construct a sequence where the zeros, big blocks of zeros and one alternate. Each time the size of the block is of an order of magnitude bigger than the previous one, and so what you see is the statistics is really oscillating, right? So you get a point that is spending a lot of time near 0, but then much more time near 1, near 1 point and near the other point. Okay, so the convergence of this is absolutely not obvious at all. In very good situations and pretty much any dynamical system you know that is not just a contraction, you are likely to find some exceptional, generally exceptional points where you may get the non-convergence of this system. There's also a, you can also construct a more geometric example like this. This is sometimes called Bowen's eye. Bowen's eye, in which you have a kind of 2 fixed points here, and then you have trajectory moving on these curves here, and this is the point P, and this is the point Q, and it's possible to construct this example. It's a delicate construction. You need to choose the eigenvalues of these two saddle points in a good way, but you can construct it exactly having these properties. So when you look at the neighborhoods of P and Q, you see that these points spend a long time near Q, and then they come back to P, but they spend an order of magnitude longer time near P. So after a while, it looks like they spend all their time near P, and then they go back to Q and they spend an order of magnitude longer time near Q, and so on. So depending on the scale, on the time scale, rather than the statistics converging, so the alternative is that the statistics might converge so that it's spending half the time near P and half the time near Q, right? So that is of course a possibility. This example, changing the eigenvalues here, you can also construct it so that this happens. This is a case where you never know, right? It's not converging to saying that you spend certain proportion of time here and certain proportion of time here. The proportion changes. So I'm only emphasizing this because somehow I'm emphasizing the pathological nature of the lack of convergence of this. I'm trying to emphasize how the lack of convergence leads to a very strange and surprising thing. It's as though when we flip a coin, right, instead of converging, the longer you flip and the closer you get to 50% heads and to 50% tails, imagine that the percentage of heads or tails depended more or less on the length of the trial. So if you flip a few hundred times, you get 90% heads, but if you flip a few million times, you get 90% tails, and so on, as though the result depended on the scale, on the time scale, right? So it's a kind of pathological thing. There's also examples in the quadratic map. There is Keller showed that there exists parameters A such that the one-dimensional quadratic map f of x, x squared plus A, has the property that mu n of x does not converge for Lebesgue almost every A. So this is also very remarkable. So you do not need to construct artificially. In this case, it's just a few points. In this case, it's a large set of points. Also in this case, almost every point for a very exceptional parameter, but this is a standard quadratic family. It's a very well-studied family, and this does not converge. So this is a real possibility that you don't get this kind of convergence. So, so this leads us to the question of addressing, whether this tends to converge. And this leads me to the definition of physical measures, really trying to formalize this. So let me write a definition here. So definition, for the probability measure mu, let mu be a probability measure on M, okay? So we let B mu is equal to the set of points X such that this sequence, such that mu n of X converges to mu. So this is sometimes called the basin of the measure mu, or basin of attraction in some sense. This is the basin of mu. So we can change a little bit the way we give this definition. Rather than trying to look for points for which this converge, we fix some probability measure and we say, okay, are there some points, this is X in M, are there some points for which this converges to this specific measure? Of course, in general, this may be empty, probably if you just choose a measure. And we say that mu is a physical measure if the Lebesgue measure of B mu is positive. It does not have to be, actually. There are examples of physical measures where mu is not ergodic, although intuitively and generally it's ergodic. So what this says is that the reason why it's called physical is because the underlying philosophy, let's say what I'm talking about, is that you're trying to describe a set of positive Lebesgue measures. Right? Lebesgue measure is our reference measure, so the point of view we're taking is that we want to understand the dynamical system, we want to understand the orbits of a positive Lebesgue measure set of points. So of course there are many other probability measures that are interesting in dynamical systems, and they have their interest in different ways, but in this case, this means that we have, to some extent, successfully started describing the dynamics. And then we can give a precise formulation of the Pahs conjecture, well, almost precise formulation of the Pahs conjecture, which is that typical dynamical systems have a finite number of physical measures, have a finite number of physical measures, mu1 to mu L, okay? And the Lebesgue measure of the union of their basins is equal to 1, so has full measure. If you assume that the Lebesgue measure on the manifold is normalized. So the only thing that is not precise here is what I mean by typical, and there is a little bit of space for negotiation there. And there are various ways to define typical. I will not go into that because this is not the focus of my lectures, but I want to give an idea that this is, in some sense, the spirit of this is that if you have a dynamical system, and this is true, that means that for Lebesgue, almost every point, so if you just pick a point at random, then there's only a finite number of statistical distributions it can have. So in some sense, it is regular, in some sense. There are examples of systems that do not satisfy that, so let me just give very briefly. So examples, again, or let me start with some counter examples. So there are examples that fail this condition, right? So basically the ones I've already given, right? So Bowen's I fails this condition because here you have a positive Lebesgue measure set of points, all the points inside here, essentially, except maybe there might be a fixed point here to make this coherent, but all these points, they're physical, these averages do not converge, right? And so there cannot be a physical measure. There's no physical measure that attracts all these points in the basin. And the same for Keller, right? Keller says that for Lebesgue, almost every point, these averages do not converge, so there cannot be a positive Lebesgue measure set of points that converges to any measure, right? You cannot find any measure for which this has positive measure because this does not converge for Lebesgue. So there are counterexamples. There are systems that do not have positive measures, do not have convergence. There's also some kind of simpler counterexamples. For example, the identity map. Okay, the identity map is in a kind of very trivial way, also does not have a physical measure. It is not as pathological as this, because in this case, these mu and x do converge, but of course for each point it just converges to the Dirac measure, right? For this we just have that mu n of x converges to delta x for each point, and therefore each point does its own thing, and there is no measure that attracts a positive Lebesgue measure set of points. So there's several ways in which the physical measures may fail to exist. either something like this where this converges, even a rational rotation also does not have physical measures for the same reason, because everything, there's an uncountable, in some sense, set of limit points for this, or you can have these more pathological things where the averages do not converge, or you can also have systems where you have an infinite number of physical measures, like the Newhouse phenomena, if some of you are familiar with this, where you have an infinite number of attracting periodic points, so you can have an infinite number. But this is just to show that there are examples where this fails, so the typical is important. This is not about saying that this happens for every point, okay? And there are, however, of course, many examples in which this does hold, and again, if F is a contraction mapping, then clearly you have that with a fixed point P, right, F of P equals P, and then you have, of course, that the basin of the Dirac delta in P is equal to the whole space, right, because everything converges to the fixed point in P, so that means that for every point converges to the Dirac delta, so this is, of course, a physical measure. The second important example is when mu is invariant, ergodic, and absolutely continuous with respect to Lebesgue, because then the invariant and ergodicity implies, as we said before, that the basin has full mu measure, right? If it's invariant and ergodic, then mu almost every point converges, so the basin has full mu measure, and then the fact that mu is absolutely continuous, just by the absolute continuity, this implies that the Lebesgue measure B of mu is positive, right? So a very important class of physical measures are just invariant, ergodic, absolutely continuous measures. And finally, perhaps what is most important is yes, the existence of physical measures. No, I'm kind of talking about the existence of physical measures, sorry. Examples of physical measures and counterexamples of lack of physical measures, yes. And then finally, a class of maps that is a kind of a class of measures as a kind of combinations, which I will not define, but the so-called Sinai-Ruelle-Bowen measures. SRB measures, which are in general, if you have an attractor, if you have some attractor lambda, this attractor will generally have zero Lebesgue measure, a little bit like in this case when you have a contraction, but it may not be just a fixed point, it may be a non-trivial attractor with some hyperbolicity, okay? And so any invariant ergodic measure will be sitting on this attractor, but it cannot be absolutely continuous because this will have zero Lebesgue measure. And so Sinai-Ruelle-Bowen measures are a way of describing the structure of measures which have some absolute continuity along some foliations, which I will not describe in detail now. And then you have some stable leaves that converge here, okay? And this makes it a physical measure. So I do not at the moment want to describe it, but let me say that in fact these are in some sense the most important for our setting, because this is the kind of thing you get when you have hyperbolicity. This is really the structure of the measure that you generally get when you have some hyperbolicity. Okay, are there any questions? Please do not hesitate to stop me or ask me if you have any questions at any point. Okay, so this is a little bit of describe this part of the first diagram, right? So I've defined what we mean by physical measure, and I hope I've kind of motivated why we would be interested in this, because having physical measures, the Pahs conjecture is that you have a finite number of physical measures that describe Lebesgue almost every point, a bit more precisely. It probably would be even more interesting if it's false. Under certain definitions of typical, it is known to be false, so you have to be, it depends very much on what you mean by typical. And certainly, in any way, I see it as a very interesting point of view, a very interesting direction of research. Okay, so let me now introduce the notion of hyperbolicity, which is going to be our way into these measures. I will describe a little bit some of the results which have been obtained using hyperbolicity. And why hyperbolicity is important for the existence of physical measures. So I will give a very heuristic definition of hyperbolicity because otherwise it will take most of my talks. So let me define hyperbolicity. So heuristic definition. And then, as I said, there are many ways. So the fundamental concept of hyperbolicity is that we have, suppose we have some subset, possibly some invariant subset, although there are situations where you talk about some hyperbolicity properties even for non-invariant sets. And the key point is that when you look at the derivative, you have a splitting. So if you look at the derivative of the tangent space over M, okay, at points of lambda, this splits into two subbundles, which are dF invariant. And such that in a kind of a, let me write it like this for the moment and say limit as n tends to plus or minus infinity of 1 over n of log of the derivative restricted to the stable subbundle is negative, and similarly the limit plus or minus 1 over n of the log of the derivative restricted to this subbundle is positive. So what this says is that if you take a vector in the stable subbundle and you apply this derivative, say for positive n, so in future time, okay, so you look at the rate. What this says is that the fact that this is negative says that this basically goes like e to the minus lambda n, or some lambda. So what this is saying is that if you take a vector es, it is contracting exponentially fast in forward time and expanding exponentially fast in backward time. And these vectors in EU, they are expanding exponentially fast in forward time. So what the hyperbolicity emphasizes is the fact that you have exponential behavior according to the derivative. This turns out to be a key point. So there are many different ways. So the limits, there are many different ways in which you can change this definition. So let me put first the second, which is also important, which is the limit 1 over n of the log of the angle between, this is also as n tends to plus or minus infinity, of ES and EU fnx equals 0. So this splitting, this set does not need to be compact, and this splitting does not need to be continuous. In general, the splitting is just measurable. So there might be points in which the angle, even though the tangent space can be written as a direct product, the angle between the stable and unstable subspaces in that tangent space may be arbitrarily small in this general definition. And so if you look at the angle along an orbit, it might degenerate, it might get smaller. What this says is that it degenerates at a sub-exponential speed. So it cannot degenerate too fast. So there are two fundamental conditions to hyperbolicity that are that you have exponential behavior of the vectors inside these subspaces, and the splitting itself instead has a sub-exponential behavior. So there are many ways in which you can, you can make this even more general. The fact that these limits exist is not necessary in a lot of results, but if you write it without these limits, then you need some additional technical conditions, so it's easier for me to write it this way. But of course, it's not natural, even though a posteriori, if you have an invariant measure, then you know that these properties, by some general results, these limits do exist in very general situations. You can make this definition stronger by assuming that these limits converge uniformly. So there is a lot of scope for very non-uniform behavior in this, because what it's saying is that at every point of lambda, these limits exist, but the convergence to the limit may be very non-uniform. So if you choose a point x, what this is saying is that eventually these vectors are shrinking exponentially fast. But for a particular x, you might see that for a finite number of iterates, you take a vector in here, and it's actually expanding, or at least it's not contracting. And this is a very fundamental point. So the fact that it's expressed as a limit says that asymptotically this happens. And asymptotically, when you have a set of points, it might be that for some points, this asymptotic behavior is reached much earlier than for other points, okay? And the fact that this may be, you might have to wait arbitrarily long for some points is part of the really profound difficulty in proving theorems for this very general so-called non-uniformly hyperbolic or just hyperbolic setting. We have a very special case, so we say that lambda is uniformly hyperbolic. So lambda is, yes? You're right, I should have said for all x in lambda, we have this property. Is that what you meant? Yes, you're right, thank you. So lambda is uniformly hyperbolic. Okay, basically if this convergence is uniform, so if convergence is uniform, heuristically you can think of it as saying that you do not need any convergence. So, well, maybe it would be better to say if you see this immediately at every step, right? So when n equals 1, you take a vector and it contracts. Okay, so you don't have to wait any amount of time, or you have to wait some finite uniform amount of time for every point. Okay, that's exactly what the uniform means. And if the angle is bounded away from 0, so angle between ES x and EU x is larger than some constant independent of x, and the splitting is continuous. ESX is continuous in x. Okay, so it turns out actually that in most cases these two properties, they can be proved from the uniform. The key point is that this is uniform. When you have this uniform convergence, then it kind of, these estimates, they pass to the closure, so you can basically show that the angle and the continuity, they follow from these uniform estimates in many cases. Okay, so there are also many intermediate levels of hyperbolicity. So you may have, for example, a situation where the splitting is continuous. You assume the splitting is continuous. One of the biggest, there's various difficulties in this most general setting, but if you assume the split is continuous and the angle is bounded away from zero, and then you can say, okay, we have a better geometric situation, but we still assume that we have some kind of non-uniformity inside ES and in U. So that is sometimes a version of partial hyperbolicity. Okay, so there are various versions. There's also a version of partial hyperbolicity that includes a three-way splitting where you have a central subbundle where you do not assume exponential behavior. So there is a large variety of hyperbolicity. Okay, so that's why I said that this hyperbolicity really there's a lot of flexibility, but the fundamental spirit is really that you have something like this, that you have exponential behavior and this some kind of bound on the angle. Yes, if you uniform hyperbolic means you have uniform. The best way to think of it is simply that if you take a vector, it contracts immediately after one iteration and it expands in the unstable bundle after one iteration. So, well, in general, you can prove if you do that, then you can see that this uniform, because you've got uniform estimate, it basically generally implies that the angle, you can kind of pass to the limit and you continue to have those uniform estimates, which means that the angle is bounded. So in general, it's once you have the uniform estimates, you kind of get the angle and the continuity of the splitting as a consequence, heuristically. Okay. Oh, sorry, the second point. No, so the second point is an important technical condition that you need to be able to prove anything, basically. So I will talk a little bit, one of the key results that you prove under these assumptions of hyperbolicity are that you have stable and unstable manifolds at every point of a hyperbolic set. And to prove that, you also need to show that this angle does not degenerate too quickly like this. It is a reasonable assumption because, as I said, when you do have an invariant measure, then almost every point, if you have this splitting, then this is automatically satisfied, if you have an invariant measure. But if you just start with an assumption of the set, you don't know. You might, perhaps, although I don't know any examples, I'd be very curious. I don't know. So does anyone know if there are examples of a set that satisfies this but does not satisfy this condition on the angle? I don't, huh? No, just an invariant set that has this, that has non-zero Lyapunov exponents in this sense, but has a, more strongly degenerating angle. I don't think there's any example is known, so I don't know if they're independent conditions or not. I don't think this is really known. In principle, they're independent conditions. One that satisfies, not necessarily with the limit, but you have this kind of exponential contraction, but along the orbit, the angle degenerates, may go to zero exponentially fast. This is saying that the angles along an orbit, the angles between the subspaces may degenerate, but not too fast. I have no idea. Maybe you can, maybe. I think that would be interesting to see that you can get one without the other, actually. I don't know of any example where you do that. Yes? Well, usually if you talk about the compact case, that basically means that the angle is uniformly bounded away from zero, so you don't have a problem, yes. So this problem arises when the angle can become arbitrarily small, right? And so if it can become arbitrarily small, then you're interested in how small does it get along a specific orbit. So there's two different things. You have your set, lambda. In the closure of this set, this splitting may degenerate, so it may not exist at points in the closure, right? That's the point of the fact, when I say that this is just a measurable splitting, this may be just a measurable set. The reason, in general, you might not be able to extend this splitting to the closure of this measurable set, because there are points in this measurable set where this is arbitrarily small, so in the closure, there is degenerate. Like when you have tangencies between stable and unstable manifolds, that's when you fail to have this splitting, right? But so we still think of hyperbolic in this most general sense, points which in the closure might not have the splitting. It doesn't matter. We just look at the points where we do have the splitting. But the splitting can be arbitrarily small, and along an orbit, you may imagine that this splitting gets worse and worse and worse and worse. And the question is, you look at the angle and you measure it, may it be getting worse at an exponential speed? And this is saying no. This is part of the assumption that this is not. But this is getting a bit more technical than what I want to get. And I've got much, much less far than I was hoping to get, of course. But still, let me, now I can't remember what time I started. Sorry? It's over. It's over. I'm done. Okay. So, so let me just conclude. So this was really the really basic background that illustrates those three concepts. Okay, so this is in some sense the introductory lecture that I wanted to talk about. So this is the concept of hyperbolicity. Okay, there are many results that say if you assume some level of hyperbolicity, I discussed there's these various kind of conditions, then you have physical measures. There is a big literature starting from Sinai-Ruelle-Bowen in the 1970s, who really pioneered this for uniformly hyperbolic systems, okay? And then there is a lot of literature going to some very recent results today. And the challenge, however, is to take a dynamical system and to show that it satisfies these hyperbolistic conditions. Okay, because then that's how you're going to prove that those class of dynamical systems. And so this is what I'm going to talk about for the remaining lectures. Okay, thank you.